Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is basic properties of vector space isomorphisms. So in a previous lecture, we did talk about isomorphisms in a previous video, but let me remind you quickly what an isomorphism of two vector spaces are. You have two vector spaces over the same field F. When we say over the same field F, that means that the scalars are from the field F. For the first-time viewer, F can just be the real numbers, but they could also be the complex numbers, the rational numbers, or a finite field such as integers modulo P, where P is a prime, or any other kind of a general field. But scalars, think of them as real numbers if you like to. So if you have two vector spaces, and if you have a function from one vector space to the other, then this function is called an isomorphism of vector spaces. We don't say of vector spaces in a linear algebra context because we know that's what we're talking about. But in algebra in general, there are other algebraic objects and they have their own isomorphisms. And in fact, in mathematics, almost every algebraic, any kind of object has an isomorphism. And so when it's not clear, we've got to say that we're talking about isomorphisms of vector spaces. And an isomorphism of vector spaces is a map that's a linear transformation. That means that T of x plus y is T of x plus T of y, and T of alpha x is alpha T of x, where alpha is a scalar, x is an element of the vector space V. The map goes from V to W. V is the domain, W is the codomain. But also, T is 1 to 1 and onto. No two elements go to the same place, and everything in W is hit by some element of V. If we have an isomorphism from one vector space to another, then we say the two vector spaces are isomorphic. So isomorphic vector spaces are vector spaces where we can find an isomorphism from one vector space to another. We like to make up words that makes us feel smart, and so isomorphism is a nice word, as is isomorphic. When two vector spaces are isomorphic, the notation that I use and often is used is to write V is isomorphic to W with this notation, with an equal sign with a squiggly line on top of it. Okay, so what is an isomorphism? The way to think about it is that isomorphisms are those maps, those functions are translations. They're ways to translate from one vector space to another. So V and W are again vector spaces. Think of an isomorphism as a perfect translation, a way of perfectly translate statements in V to W. Well, for one thing, we want so that's what the translation map is. We want the map to be 1 to 1 and onto. We want it to be 1 to 1 and onto because we want a perfect translation. We want to know for every word, every element of V, what's the corresponding element in W, and we want to be able to go back and forth. If I give you an element in W, you know exactly what it came from, and any element from V goes exactly to one element, and no two elements go to the same place. And every element in W comes from some element of V. That's the 1 to 1 and onto-ness. And because it's 1 to 1 and onto, the function will have an inverse, and there's a way of undoing and coming back from W to V. But that's not enough, because we also want linear algebra properties to be translated, not just that we can translate every element from V to W, but we want to have the linear algebra properties to be translated. So what does that require? Well, if V1 is an element of the domain V, then it's mapped to something by this map, T of V1. And if V2 is another element, it's also mapped to another element in W, T of V2. But V is a vector space. That means we have addition and scalar multiplication. So for among other things, we can add the two vectors, V1 plus V2, and we get another element of V. So where should that go? Where should that element go to? Can I send it anywhere I like, or are there restrictions? And what I want is, I want V1 plus V2 to correspond to T of V1 plus T of V2. So I want to send V1 plus V2 to T of V1 plus T of V2. And so one of the requirements is that to preserve the addition property, I want for all vectors in V1 and V2 in V, upside down A means for all, I want T of V1 plus V2 to be T of V1 plus T of V2. But I also want the same thing for scalar multiplication. So if I take one of these vectors and multiply it by scalar, that shouldn't just go to a random place either. It should go to alpha times the image of that vector. So T of alpha V should be alpha T of V for all vectors in V, and for all alpha, which are scalars. And in this case, I'm writing them as real numbers. Okay. So the advantage, and these two last properties are exactly the linear transformation properties. If a function that just has these two properties, T of V1 plus V2 is T of V1 plus T of V2, and T of alpha V is alpha T of V, is a linear transformation. So an isomorphism is a linear transformation that's also one-to-one and onto. And we have talked about linear transformations in previous videos. One of the things it does is that it takes linear combinations to the linear combinations of the images. And because of that, if you have a statement, a linear algebra statement, something like all these vectors linearly independent. If you translate over to W, if you have an isomorphism, then you can ask your question over there in W and get an answer, and the answer will be right, and you can translate your answer back to V. So an isomorphism preserves addition and scalar multiplication, and you can translate any linear algebra question, because linear algebra questions are all about addition and scalar multiplication. That's all what a vector space has. It has an addition, it has a scalar multiplication, and they follow certain rules. And because linear transformations preserve addition and scalar multiplication, and because the map is one-to-one and onto, you can translate any linear algebra question without any change to another one if you have an isomorphism between them, and you using that translation, the isomorphism map, and then you can get your answer in the new vector space, and you can translate the answer back. To isomorphic vector spaces, we think of them as the same vector space as far as linear algebra is concerned. They might look different, they might have different looking elements, and they might have other properties that are not linear algebra properties. But if you focus on the linear algebra properties, things that have to do with addition and scalar multiplication, the two vector spaces are going to be identical, and we think of them as the same. Now, that's a heuristic, and that's not a theorem, but one that for every possible property, if you think of, okay, is this a linear algebra property or not? If it is, then you should be able to prove that two isomorphic vector spaces, if one has that property, then so does the other, and vice versa. Why is this important? This is very useful because in some vector spaces, calculations are easier. For example, in Rn, in n tuples, we can do lots of calculations because they're numbers and so on. And some other vector spaces, their elements are not n tuples, and they're harder to do calculations. And so this idea that we can translate from one vector space to another, it's going to be very helpful in that way. So let me give you a quick example. So W is a bunch of matrices. It's a subspace of 2 by 2 matrices with real entries. So it's not all 2 by 2 matrices with real entries. It's some of them. Which ones? The ones that look like this. The one entry of the matrix is a 2 by 2 matrix, can be anything you like. And the row 2 column 1 entry can also be anything you like. But then the second columns are not arbitrary. So the top entry is 4a plus 7b, and the bottom one is a minus b. What's bb is some other real number. So I've got a and b and c are real numbers, and you plug whatever you like in there, and you get elements of this subspace. So what I'm going to do is that I'm going to now give you a map from polynomials of degree less than or equal to 2 plus the zero polynomial to W. So T is a function that takes a polynomial, that's its domain, and gives you one of these matrices. How does it do that? Well, here's the rule. If you give it the polynomial a plus bx plus cx squared, then you get a for a plus 7b, c, and a minus b. And because P2R is the domain, I have to be able to plug in every polynomial of degree less than or equal to 2. And that's why I gave you a rule that tells you how to send every arbitrary polynomial of degree 2, whatever a, b, and c are, it doesn't matter. This rule tells you how to do it, to send it over and get one of these elements of W. Okay, now, so what? So first of all, you have to check that this is a linear transformation. We have in videos on linear transformations, we have done examples of such things. In the future, we'll actually have better ways of thinking about this when we translate all linear transformations from finite dimensional spaces to finite dimensional spaces to matrices. Then we will have, that was spoiler alert, we will have better ways of checking whether or not this is a linear transformation, and you can check that. But after you check that, then you have to also check that it's one-to-one and onto if you want to see if it's an isomorphism or not. It's onto, the onto-ness is clear because the typical element of W is hit. If you tell me, if you give me an A, B, and C and tell me, okay, here's the element of W, where does it come from? I'll just plug it in here, and that same A, B, and C will tell you exactly what polynomial to send there. So the fact that it's onto, it's clear from the definition of T. So the only other thing I need to prove to show you that this is an isomorphism is to show that it's one-to-one. Now, so I can actually write down, I didn't need to do this, but I wrote down what W is. W is a span of these. How did I get these? I put A equals to 1, B and C equals to 0, B equals to 1, A and C equals 0, and C equals to 1, and A and B equals 0, and I got these three vectors, these three matrices, which are vectors because W is a vector space, these three matrices in W. And so these are in W, and they span W because they're linear combinations, is that typical element of W. And it's easy enough to check that they're linearly independent because the first one is not the zero vector, and the second one is not the linear combination of the first, and the third one is not a linear combination of the first two. So this is a basis for W. And because this is because T is onto, this is also a basis for the image. I could have also sent in a basis for P2R over to get a spanning set. And in fact, if I use the basis 1x and x squared, I would have got exactly this spanning set for the image. So this is also the image. So that tells me the rank of T, which is the dimension of the image, is the same as dimension of W, is 3. Why did I find the rank? I was going to try to find that the T is one-to-one, and I could have directly show you that T is one-to-one, but I don't like to do extra work because we have something called the rank nullity theorem, a very important theorem of linear algebra and subject of a separate video altogether, that says that rank of a linear transformation, which is the dimension of the image, plus the nullity of the linear transformation, which is the dimension of the null space, is always equal to the dimension of the domain. So this says that by the rank nullity theorem, I can find the nullity because the nullity plus the rank is the dimension of the domain. The domain is P2R, its dimension is 3, but the rank was already 3, so that tells me that the nullity must be 0. Now, nullity is the dimension of the kernel, and we know that if the dimension of the kernel is 0, that means the kernel is 0, and linear transformations have this wonderful property that you can tell if they're one-to-one just by looking at the kernel. And so this says that T is one-to-one because the kernel is just the zero vector, T is one-to-one. You might wonder why. Well, you should watch the video on kernels where it goes into much detail about the fact that kernels control one-to-oneness. So because the kernel is just the zero vector, and I get that because I know that the nullity is 0, T is one-to-one. And so T is an isomorphism. So T is an isomorphism from polynomials of degree less than or equal to 2 to W. So now we know that these two vector spaces, even though they look different, P2R consists of polynomials, and W consists of 2x2 matrices. These two, and it's not all 2x2 matrices, this particular set of 2x2 matrices, these two spaces are isomorphic. And as I said, as far as linear algebra is concerned, they are really the same. Now, there are things you can do with polynomials that you can't do with matrices. Like, for example, if you take 2 degree 2 polynomials and multiply them, you will get a degree 4 polynomial. That's a very different thing than, say, matrix multiplication. I can also multiply matrices 2x2 ones and get another matrix. It's not clear if you multiply. In neither case, when you multiply them, it's not clear that you will get something else in W. Multiplying neither matrices or polynomials is part of linear algebra. I mean, we use those things and we do those things, but they are not the defining aspects of a vector space. So those are not linear algebra questions. Whether or not multiplication polynomials and multiplication matrices correspond, they don't in this case. But as far as linear algebra is concerned, as far as things like bases and as far as linear independence and spanning and those other kinds of things, these two vector spaces behave identically. Okay. All right. So now I want to show you some properties of isomorphisms. First of all, if V and W vector spaces, Isomorphism goes both ways. You can go back and forth. So if there is an isomorphism from V to W, meaning that if V is isomorphic to W, then T inverse is also an isomorphism. T inverse is the inverse of T and goes from W to V. Now, not every map has an inverse, but isomorphisms always have an inverse. So let me remind you what inverses are. This is in general not about just vector spaces, just about any functions. If you have two sets, and if you have a function from A to B, then another function, G, is the inverse of F. If when you compose it with F, you get the identity. So if you do F first, then G, you get the identity map on A, meaning, and if you do G first and then F, you get the identity map on B. And all that means is that G is the undoing of F. If you do F, then G, if you do G, then you got back where you started. If you start with G and do G, and then you can undo that with F. F and G are undoing of each other. Now, not all functions have such inverses, but they do. F has an inverse if and only if it's one-to-one and onto. You need both one-to-one and onto-ness to have an inverse. And if you have an inverse, you will be one-to-one and onto. This was also a subject of a previous general lecture on functions. Okay, so in our case, when we have an isomorphism, isomorphisms are one-to-one and onto, so they do have inverses. So T inverse is T inverse is exists. But I have to what I want to show you, what this lemma says, is that it's also an isomorphism. And one way to think about this is that if V is isomorphic to W, then W is isomorphic to V. Now, if you think of isomorphic vector spaces as the same, then of course that makes sense. If V is the same as W, then W is the same as V. But that's, as I said, an intuitive way of thinking about isomorphisms. Is not a proof that that's the case. We have to prove it, which I'm going to do next. So I'm going to try to prove that if T from V to W is an isomorphism, then its inverse is an isomorphism from W to V. Well, as I said before, because T is one-to-one and onto, T inverse exists and is also one-to-one and onto. Why is that? Well, because T inverse also has an inverse. What's its inverse? T. When you have a map that's one-to-one and onto, it has an inverse, and the inverse will have an inverse also, because that will also will be the original map, and because of that, it will be one-to-one and onto. Okay, so I know T inverse exists and it's one-to-one onto. I have to show that it's a linear transformation. So that's what I need to show, that T inverse is a linear transformation. So what does that mean? So I'm going to pick the T inverse goes from W to V. So I pick two arbitrary elements in the domain of T inverse, which is W. And what I need to show you is that T inverse of W1 plus W2 is T inverse of W1 plus T inverse of W2. T inverse of W1 plus W2 is T inverse of W1 plus T inverse of W2. And I have to do the same thing for scalars. Scalars often get shortchanged because their proofs are similar. And if I do one, you can do the other one. Okay, so how am I going to do that? First of all, I'm going to say T is onto, because it's an isomorphism. So this W1 and W2, which were elements of W, came from somewhere via T. So there's some V1 in V and some V2 in V also. Backwards E means there exists a V1 and a V2 in V, with the property that T of V1 is W1 and T of V2 is W2. So V1 and V2 are the two elements that ended up in W1 and W2. Okay, so what about it? Well, let's think about it a little bit. V1, T takes V1 to W1. Well, then that means T inverse, which was the inverse of T, the undoing of T, does the opposite, takes W1 to V1. That's what the definition of inverse tells us, that T inverse is doing the opposite of what T did. T sends V1 to W1, T inverse will send W1 to V1. Likewise, T sends V2 to W2, so that's the same as saying T inverse is saying W2 to V2. Okay, so now where does V1 plus V2 go? Well, it goes to W1 plus W2. Why? Because T is a linear transformation. But if T sends V1 plus V2 to W1 plus W2, then T inverse, which is the undoing of T, must send W1 plus W2 back to where it came from, which was V1 plus V2. But if you read what this last sentence says, it says that T inverse of W1 plus W2 is V1 plus V2, but V1 was T inverse of W1 and V2 was T inverse of W2. And therefore I proved that T inverse of W1 plus W2 is T inverse of W1 plus T inverse of W2. And scalar multiplication is similar, and this proof is done. So the final properties of isomorphisms that I want to tell you are what are sort of equivalence relations. This says that isomorphism is, if you know what that is, an equivalence relation. So U, W, and U are vector spaces. And then if I know that V is isomorphic to V, again, if you think of isomorphism being the same, then this is obvious. Of course, the vector space is isomorphic to itself. But our definition doesn't say, like, think of it that way. It says, give me an isomorphism. So what's an isomorphism? A one-to-one onto linear transformation from V to V. It's the identity map. What's the identity map? The very boring map that sends every element to itself. That map is an isomorphism. It's clearly one-to-one onto, and it's a linear transformation. And so because of that, every vector space is isomorphic to itself. The second one is that if V is isomorphic to W, then W is isomorphic to V. That's what we just actually proved. So if T is an isomorphism, that's what it means to say V is isomorphic to W, then we proved that T inverse that goes from W to V is also an isomorphism, and therefore W is isomorphic to V. That was the subject of the previous slides in this lecture. And the final thing is transitivity. If V is isomorphic to W and W is isomorphic to U, then V is isomorphic to U. Not all relations are like that, but isomorphism is like that. This is what makes this one of the things that makes it an equivalence relation. So how do we prove that? Well, what does it mean to say V is isomorphic to W? That means there's an isomorphism from V to W. What does it mean to say that there's an isomorphism from W to U? W and U are isomorphic. It means there's an isomorphism from W to U. And so maybe T is the isomorphism from V to W, and maybe L is the isomorphism from W to U. Then we have an irresistible urge to compose them and look at L circle T. L circle T is the map you get by doing T first and then L. You do T and then L, and the resulting map goes from V to U, and it's L circle T. And in previous videos, we have shown that if you have a bijection, if T and L are both one-to-one and onto, in fact, if T and L are both one-to-one, then L circle T will be one-to-one. And if T and L are both onto, then L circle T will be onto. So if they're one-to-one and onto, then L circle T will be one-to-one onto as well. And also in the lecture on linear transformations, we proved that the composition of two linear transformations is also a linear transformation. So if T and L are isomorphism, they're both one-to-one and onto and linear transformation. So by what we have proved before, their composition is also one-to-one and onto and a linear transformation. And therefore, it's an isomorphism from V to U, making V isomorphic to U. Okay, so what is going to happen next? Well, we will define in the next lecture that comes right after this one. We define coordinate maps, and that will give us a rich collection of isomorphisms. So they go from n-dimensional vector space V to Rn or to Fn if the field of scalars is different. So we define those, and those will be we will show that they are always isomorphism, and this will be again a rich collection of isomorphisms. And the reason that will be really important is that in the next video we will see that there will be far-reaching consequences of that, because then that will say that there's many vector spaces that we were working with that we thought were different, but now they're all isomorphic, and therefore we can do our translation project, which will be the subject of future videos, where we translate from one vector space to another, ask our questions there, and then translate back. This is the end of this video. Keep hydrated, and we see you in the next video.